So very good morning to you, okay? And we have been working on non-degenerate perturbation system, and we have actually obtained the basic formalism of time-independent perturbation non-degenerate theory. So let me give you an overall view of non-degenerate perturbation, and then probably we will try to take a problem where we will introduce a kind of perturbation, and we will try to calculate the correction. We'll calculate the correction to energy, and we'll try to calculate the correction to the wave function. So it all depends on the time. The time should allow us to do that. So this is the title, and we'll be talking about this non-degenerate perturbation theory, and we'll be talking about some of its important applications. Probably when you go into semester 9, you will come across advanced atomic and molecular physics. There, the role of this non-degenerate perturbation theory, this perturbation theory in general, which is independent of time, you will find its application there in atomic and molecular physics. So to introduce you, the point is, what is perturbation? Perturbation is that you are introducing a small disturbance to the system. The system is ideal. The system is calculable. You can calculate the energy values of the system, and you can calculate the energy eigen vectors of that system. But once you introduce a small disturbance to the system, so that there is not the drastic change in the system itself, the disturbance that you are introducing in the system has to be extremely small. And to make the mathematical formulation and calculate various things for the concerned problem, we can make use of the perturbation theory. And you understand it, that why do we need it in quantum mechanics? Because in quantum mechanics you have a range of problems which cannot be exactly solved. You cannot solve those problems exactly. So that's why you need an alternative approach where you can at least have an information about the system. So we have two types of perturbations. We have time dependent and we have time independent. So in this talk, I'll be only talking about the time independent non-degenerate case because this is the focus of our lecture, and obviously we have developed the basic formalism for time independent non-degenerate case. Now, as I said, that in real world, in real quantum world, I believe everything is quantum mechanical in the universe when we go to the atomic and molecular level. So in real world, what we have is we have complex problems. We cannot have exact solutions for these problems. And this perturbation theory, it really plays a role to give us an approximate solution. And as I said, this perturbation has to be small. It has not to be something that will completely distort your system. If it completely distorts your system, you cannot use perturbation theory. The important thing is that you must have small perturbation. And generally in our problems, this perturbation is introduced in terms of the potential. So we have the mathematical framework, and we have already gone through that mathematical framework, but I want to remind the whole process again. What we have is, we have an unperturbed Hamiltonian, right? And what we do is we introduce a small perturbation. If I assume that perturbation that I'm introducing is in terms of the potential of the system, then your perturbed Hamiltonian will be the summation of your unperturbed Hamiltonian and the perturbation that you are introducing into the system. And this lambda that you can see here, as we understand that the perturbation has to be extremely small, so this lambda has to be small, and this lambda will control the strength of the perturbation that's involved in your problem. So there are basic assumptions. We use those assumptions, and And what's the first important assumption is that you know everything about the system when the system is in unperturbed state. You know exactly how to solve Schrodinger's wave equation. You exactly can solve the Schrodinger's wave equation, and you can calculate the energy eigenvalues, you can calculate the energy eigenstates of the system. You know that framework completely. So the equation that you have here, this is your Schrodinger's time-independent equation for an unperturbed system. Where this N naught and N naught, you understand that in our framework we chose them as psi N naught. Okay? So this perturbation that you introduce, it has to be very small in comparison to the Hamiltonian. That's exactly solvable for our problem. Okay? That is an important parameter to be kept in mind. Right? So this is our first basic assumption, that you start your problem by a known solvable Schrodinger's wave equation where you can exactly calculate the energy eigenvalues and energy eigenvectors. And we have obtained this equation yesterday, okay? And this will give us the first order correction in the energy of non-degenerate system. Okay? And there we have H prime here. Since I have taken potential where you are exerting potential on your system as a perturbation, and the magnitude of this potential has to be extremely small. And you can see that this is merely an expectation value, right? And it can be an expectation value, or you can have a matrix where you have to diagonalize that matrix to calculate the energy eigenvalues. So the intuition here is to calculate this expectation value of perturbation. You see the framework. What's the framework here? The framework is unperturbed. You are introducing your perturbation in a framework of unperturbed system. Okay? Anything? Any questions? So the same way you can obtain the second order correction, and for you know that this m should not be equal to n, and because in the same Hilbert space you have the two different basis vectors, and you come up with your this is your first order wave function correction. We calculated it yesterday, we obtained this equation yesterday. Then this will be your correction, second order correction to your system, and as you can see, the same thing is there. You have the mod of scar divided by En minus En naught. So this equation will give us the second order correction in terms of the energy of the system, to which you are introducing what? You are introducing this perturbation. So you can tablize this. So what you do, you calculate the energy eigenvalues, you calculate En naught, En1, first order correction in energy, second order correction in energy, and so on and so forth. The majority of the values that we obtain, because as you move on in your Taylor series, you will have functions, scar functions. So the magnitude of the higher order terms is going to be extremely small. So their contribution is going to be very small. That's why the most of the calculations are taken up to the second order correction in energy of the system. Clear? So these are the corrections in terms of the energy, and these are the corrections in terms of the eigenvectors. So now, why do we use this perturbation, the non-degenerate perturbation? We use this theory in complete framework to understand the basic problems of atomic and molecular physics, and star effect is one of them. What you have a material, you apply electric field on the system, and there is splitting of energy levels, right? What is this called? This is called Stark effect. You apply the external electric field on the system. Suppose you have a single energy level. This energy level splits in a range of energy levels. This is called Stark effect. And you can explain Stark effect using a non-degenerate perturbation theory. Another important effect is the Zeeman effect. And what is Zeeman effect? Come on. Yeah, what's Zeeman effect? Yeah. Yeah. You apply the magnetic field and there is splitting of energy levels, right? And you can explain that splitting of energy levels using perturbation theory. And perturbation theory is the right choice to explain the problem of Zeeman effect, splitting of energy levels when you apply the magnetic field to your system. So what you are doing is you are basically introducing the perturbation to the system, right? You are introducing the weak perturbation to the system. So when you do that, you find something and you try to explain the splitting of those energy levels, and you can explain these splittings using non-degenerate perturbation theory. Then the fine structure. Come on, what's fine structure? Yeah. Again, you have when you use powerful microscopes to see these energy levels, say for hydrogen atom, you find that each energy level has it is splitting in more energy levels, and for that you have the reasons, what we call as spin orbit interaction. You explain the splitting of those lines. So here, in explaining the fine structure of hydrogen atom, we can think of using non-degenerate perturbation theory. And obviously, boiling down to the molecular physics, where the problems are extremely complex, where you cannot exactly solve a system where you have a bond between the atoms. So there, this perturbation theory plays a very vital role. And as I said, you introduce a perturbation if you have to explain the Stark effect. Okay, so then you can calculate and you can find where the things vanish and where there is the shift in the energy levels. Clear? Okay. Similarly, as I think I have talked about Zeeman effect. It's clear. And it does have applications in molecular physics, where you can calculate the perturbations that you introduce in terms of vibrations and the rotational motion of the molecules, and you can introduce those corrections to calculate the overall energy of the system. So in general, I would say that when you are adding perturbation to your ideal system, you are taking your system from ideal harmonic oscillator to an harmonic oscillator, right? So you take the system from the ideal framework to the real framework. So you can actually solve these problems using perturbation. It does have clear applications in solid state physics, condensed matter physics. When you take on the perturbation, you can explain the corrections to the band structure. If you rightly go back to your condensed matter physics classes, you have talked about the band structure of solids. And I believe it's Cronin-Penny model, this is the basic model of quantum mechanics, that tells us that you have the energy bands, that predicts the energy bands in the solids. But the energy bands that you are calculating using Cronin-Penny model, these are ideal energy bands. And you can introduce perturbation to your systems to calculate, because if you are introducing some imperfection to your system, you are adding, you are doping your system, what will happen to the band structure? There will be change in the band structure. So how can you explain that small change in the band structure? Perturbation theory can play a very important role there in adding those corrections to your system when you are trying to transform your system, of whose conductivity changes. Maybe the width of the band structure changes. The gap goes on, maybe it increases, maybe it decreases. You can have your calculations, you can use them to calculate those corrections to the band structure. And if you go back to the condensed matter physics, you have two types of solids. One is called a crystalline solid, and another is called an amorphous solid. And crystalline solids, what they have the long range order. And what about the amorphous? Come on. They also have order, but their order is extremely short. So they have short range order. So in crystalline solids, what you have periodicity. I mean, if you have a house made of same kind of rooms, you will move from one room to another room, you will not be able to differentiate one room from another room. So this gives birth to periodicity of the system. So you can calculate the corrections to the weak periodic potentials that are introduced in these solids. So perturbation, it is basically an approximate method for quantum systems, and you have you calculate its order by looking at the system mathematically, and it certainly has various applications in quantum systems which we have discussed till now. Okay, right? So now I want to cut it. It's not coming. Maybe something. Well, if you have any questions, you can ask me. Or tell me how to close it. Come on, come on.
Left one which chal raha hai.
Huh?
Left one which chal raha hai.
Which one? This one? This one? Come on, come on. This is so strange. Is it hanged? But it's working, no? Let us restart it. That is the right way. This is called jugaad, right? So, okay. So now let's go with the problem. Okay, let's solve a problem to understand basically what we have calculated yesterday, right? And for that, I should choose a problem. Come on. I want this. Okay. Let's choose a problem. I think we have already gone through the problem of infinite scalable potential, right? Do you remember that? You remember that? Can you tell me anything about that? Yeah. What is the problem of infinite scalable potential?
We have a particle
Yeah.
inside that and we calculate the wave function of that particle and probability of existing the particle outside this.
Exactly, exactly, right? And and we know how to solve that problem. Okay, we know how to solve that problem. We have a problem where we have an infinite potential for a particle, and you have a particle. This particle is in our one-dimensional box, right? And we have solved this problem. We have calculated the eigenfunction for this problem, and we have also calculated the energy eigenvalues for this problem. And so if I take the ideal, if I take this infinite scale well potential. Okay, for that, if I choose a one-dimensional box, and this one-dimensional box has length, say, L, and I calculate its eigenfunction, psi n, what is that? That is under root of 2 by L sine of n pi x by L. Is it so? Right? This is your eigenfunction, this is your eigenvector for the particle in one-dimensional box. And at the same time, what we do is we calculate the energy. Can you tell me how much is the energy as you calculate? It is n squared pi squared h bar squared by 2ml squared. So if you have a particle in a one-dimensional box which has infinite potential at its edges, the particle is existing in this one-dimensional box, we calculate its energy eigenvalues and we calculate its energy eigenfunctions. We assume that the length of this box is how much? L. Okay? So the length of this box is L. So this is calculated. This exactly solved problem, right? Now, what will I do is, I will introduce a small perturbation to this problem, right? I will introduce a small perturbation. So if I introduce a perturbation, if I assume my perturbation is like you have this one-dimensional box, and I introduce a disturbance like this, and this disturbance has the shape of your delta function. And if I say that if I take on this perturbation for this problem as h is equal to beta of the delta function x minus L by 2. So this is L, right? And what I do is I introduce perturbation. I introduce the disturbance to the system, and that disturbance is mathematically defined like this. And you can see that disturbance is made of some constant beta multiplied by the delta function. So the disturbance that I'm introducing here is somehow symmetrical to the delta function, right? Clear? Now what I want then, I want to calculate the correction in energy. Because I'm introducing the perturbation to the system, I have to calculate the correction in the energy. Now there are a long range of corrections. I will take my correction to the first order. And similarly, I have a well-defined wave function. Maybe we will not today get the time to go with the wave function. We will proceed that tomorrow. Then I would like to calculate the corrections in the eigenfunctions of the system where I have introduced this perturbation. Clear? Okay. So this is my disturbance that I have introduced in my system. Okay? So yesterday we calculated the first order correction in energy. What was that? The first order correction. Come on, tell me. It was E and 1. This is equal to psi n naught plus h prime psi n naught. This is it. Check it out. This is our first order correction to the energy. Right? So if I have to calculate this energy, I have to solve this problem. I have to solve the expectation value of my problem. Isn't it? Getting my point? So how do we write an expectation value? Suppose I have the expectation, say psi, say A operator and psi. So if I'm calculating the expectation of the operator A, what is it? It is an integral from minus infinity to plus infinity. Then you take the psi star here, and then you take your operator A cap, then you have psi and dx. This is how we calculate the expectation value, right? So the same thing we are going to do here, because we want to calculate the correction in the energy. The correction that has been introduced by disturbing this infinite scalar potential at its middle and representing that disturbance in terms of a delta function. So how can I write my En1? What is my En1? En1 is psi n naught, then you have h prime, then you have psi n naught. So this must be equal to integral minus infinity to infinity psi n naught. So that is under root of 2 by L. Clear? And then sine of n pi x by L. Then you have the perturbation. What is that? That is beta. Delta of x minus L by 2. Right? And then again the psi, that is under root of 2 by L, sine of n pi by L x, and then you have dx. Thank you for coming to the class. I can see you first time in the class. Okay, so E and 1, come on. E and 1, will be equal to the integral of this. Is this clear to you? Okay, so I'll write it again. I'll go on the next page. So what we have en1. So en1 is going to be integral minus infinity to infinity, and then you will have under root 2 by L whole square. Square and root will cancel. Beta will be out, so it will be beta 2 by L. This will be it. Okay? And you will have sine square n pi by x by L. And delta of x minus L by 2 and dx. Okay, right? Now we already know from the property of a drawn delta function, what we know is if you have an integral minus infinity to infinity and you have f of x, then delta of x minus a dx, this must be equal to f of a. Right? So this integral is solved. This integral is solved. All we have to do is to introduce a in your solution. But for a, what you have L by 2. Is it clear? Can I proceed now? Can I proceed? So, let's move from here. Okay, what you will have? You will have en1. So, you will have 2 beta by L, and you will directly get sine square n pi by L dot. For x, I will use L by 2. The job is done. Right. So en1 will be 2 beta by L. This L and L will cancel. And no, this 2 is outside the function sine of theta. Okay? Don't kill them. This will go against the basic laws of mathematics. Right? My son also does these kinds of mistakes in his 4th class. He cuts everything. He feels everything has to be cut. But you do mathematics only when you follow the basic laws of mathematics. So you should respect the laws. You cannot cancel this 2 with this 2. So this 2 beta by L is outside, and inside you will have sine square n pi by 2. Right? Okay. Now you will have 2 kind of situations here. Now n can be even and n can be odd. So for n even, you will get 0, right? And for n odd, you will get 1, right? So how can I write down this correction to energy as first order correction? So I can write en1, if I tabulate it, I will call this 0 for n is even. And this is 2 beta by L for n is odd. We'll stop here, okay? If you have any questions, you can ask me. Come on. You have any question? Can you?